Hello everyone, welcome to this video on field theory. In this video we shall see that embedding of any field f into a field E implies that the letter field E, that is an extension of f. So first of all, what is an embedding? Embedding, it is a map, say f from any field E to f to E, which is an injective homomorphism. That means it is 1-1 and it is homomorphism. Homomorphism, what does it do? It preserves the operation in this set or in this field and in this field. Then we call that mapping as an embedding of f into E. So let us see the next result. The result says if we have two fields E and f and we define an embedding sigma from f to E, then in that case what happens? There exists a field K such that f is a subfield of K and sigma can be extended, the given embedding, this could be extended to an isomorphism of K onto E. That means we are to show there is a mapping sigma star, say sigma star, which provides a homomorphism between these two fields K and E. So let us see what exactly the theorem says, result says. It says that if we have two fields f and E and there is a embedding between these two, that is the mapping sigma is 1-1 and homomorphism. In that case, there is a extension field K of f such that this mapping sigma, this could be extended to some other mapping, say sigma star, such that this K and this E, they are isomorphic to each other. So we are given this sigma and this is 1-1 homomorphism. So it says K is the extension of f and this can be extended to some other mapping, say sigma star, such that this mapping forms an isomorphism between K and f. This is the statement. So let us see the idea behind the proof, how we can prove this thing. So here, for the proof, we have assumed this thing that sigma from f to E is the given embedding. So we have proved this thing that this sigma from f to E, this is an embedding. That means sigma of f would be a subset of this E. Suppose this is our set E. This is the given field E. So here we say this portion, this is sigma of f, because it is given to be 1-1 but not onto. So whatever left over here, this portion, this is E minus sigma f. There is no problem writing this. So for this, what we do, we define another mapping, another set such that the cardinality of set S is same as that of E minus sigma f. We create a set S such that their cardinalities are equal. Moreover, the new created set S with the given field, they do not have any common element between them. Then we can define another map, say f, from this set to whatever is here, E minus sigma f. So such that this map is a bijection. This is also our assumption. Moreover, if we take the union of this f and s, so it will result in, so if you add this f and s, because there is no common element, so you will obtain k. So we have defined this set such that it has no common element with f, such that the cardinality of this set S is equal to cardinality of E minus sigma f. Moreover, this mapping is bijective, that means it is 1-1 and it is onto. So the union of these two is the field K. So in that case, what we have to do in order to prove this, we shall define a mapping from K to E, call that by sigma star, such that this mapping sigma star from K to E, this is a isomorphism. So in order to define this mapping, we have to define how does it map the corresponding elements? Now this set K, this field K over here, it is composed of two fields, two sets or two fields. One is S, one is F, right? So now this F maps elements to E, and this S maps elements from E minus sigma F. So overall this is some E and this is K. So we have to prove that K is isomorphic to E using this sigma star. So this is our aim. So now we can define the isomorphism. We can define this mapping sigma star such that if we take any element A from the field K, then if that A is in F, if this A is in F, then we say that the sigma star take that to sigma A, and if our A belongs to this set S over here, in that case the mapping sigma star take that to F of A, and F of A is a bijection, so it again may take the element to E. So first of all we have to check, in order to claim sigma star is an isomorphism of K onto E, we have to check whether the mapping sigma star, this is a well-defined mapping or not. So for well-defined mapping we need to check if we take any element A from K. So in that case the sigma star of A should belong to E. So we need to check this thing. So now if you take any element A from K, then this element, because our K was this was our K, it contains two parts, one is F, another is S. So now if A belongs to this part, then it would simply be sigma of A, and sigma of A is obviously, because sigma is a mapping from F to E, so everything sigma of A would land up in E. So we are in E, right? And if this element A belongs to this S, in that case sigma star of A would be F of A, and F of A, because it is a bijection from S to sigma E minus sigma F. F was a bijection from S to E minus sigma F, therefore it also land up in E. Thus the given mapping is well defined. Next thing to show for isomorphism is that this mapping is 1-1. For 1-1, what we have to show? We have to show that sigma star of A is equal to sigma star of B. What is that means if you take any two elements from K, then sigma star of A is equal to sigma star of B should give you A minus B. So now you can prove this using this definition. You again have to go for two cases. One case is that if A belongs to F, what is the case? If A belongs to F, in that case sigma star A is equal to sigma star B, and that is equal to sigma of A is equal to sigma of B by definition. And because the sigma is 1-1, therefore you have A is equal to B. If your A belongs to S, in that case your sigma star A is equal to sigma star B gives you F of A is equal to F of B. Now F of A, this mapping F, that is a bijection, that means it is 1-1, therefore it again give you this. So our mapping is also 1-1 and it is well defined. The next step is to prove that this is an onto map. For onto map, what you can do, you have to prove that every element of E has a pre-image in K, because sigma star is from K to E. So what you do, you again take an element, say L from E, and then our set E was composed of two things. One was sigma of F, another was E minus sigma of F. Now L could either go to this or to this. Now depending upon if our L goes to this part, obviously it would have a pre-image because the mapping F is a bijective mapping. If it goes to this part, then you can also prove the same thing, that it has for every element a pre-image in this. Therefore sigma star is also a onto map. So we got 1, 1, we got on 2, we got sigma star. So we got a bijective mapping. Next, in order to prove isomorphism, we should also show that the mapping sigma star preserves the operation of addition and multiplication. And for that, we have to define the operations. This is the operation which is performed in the field K, and this addition operation is being performed in the field E. Similarly, this multiplication operator is performed in field K, and this multiplication operator is performed in E. So before that, we have to define these operations for the given mapping sigma star A. So this operation, what is this? It says that if you take any two elements in K, now we are talking about sigma star from K to E. If you take any two elements from K, then their addition in K would be defined as sigma star inverse sigma star of x plus sigma star of y. Sigma star of x obviously would land up in E. Therefore, these two elements are being added in E. So whatever is here is in E. When you take the inverse image of the element over here under the mapping sigma star, you land up at K. So obviously these operations are performed in K. Similarly, for multiplication, we defined the operations like this. So you can easily prove for an homomorphism that when you perform the additions in K, that is equivalent to additions in E. Similarly, when you perform the multiplications in K, they are equivalent to that in E. So we also reach at a homomorphism. Therefore, as all these conditions are satisfied, therefore our mapping is isomorphism. Hence, we can say the extension of F, that is K, this is isomorphic to E, where this F to E, this is an embedding. This is given to us. So let us sum up the result of this theorem by seeing that whenever sigma from F to E is given to be an embedding, then we can identify any element of F with that of sigma F in E. How to do that? Because we have just seen that we have this extension K of F, and these both are isomorphic to each other, right? So we can identify any element of F with sigma F by writing X associated with sigma of X. So in this case, we can say that the mapping E is also an extension of F. Earlier we had K to be the extension of F. Now E is also an extension of F. So whenever we have an embedding between two fields, in this case, this field is an extension of the previous field. So finally the result says whenever there is an embedding of field F into field E, we say that E is an extension of F. Well, that is it for this video. Thank you so much for watching.